So we've made this definition that an orthonormal basis is a basis where the dot product between any two vectors in the basis is 1 if it's actually the same vector that you're dotting with itself, and it's 0 if you have different vectors that you're dotting with themselves. This first property is just telling us that the magnitude of each vector in the basis is 1, and the second is telling us that if you have two distinct vectors that you've taken from this basis, then they're perpendicular to each other, or they're orthogonal. The thing about what makes orthonormal bases so nice is that they have some nice properties, right? If this property of a basis didn't give us some nice things, we wouldn't bother giving it a name. So let's look at the nice properties that orthonormal bases have. So the first nice property of an orthonormal basis is that it's very easy to compute coordinates in an orthonormal basis. And this really is what inspired us to make the definition of an orthonormal basis to begin with. So if you think about in general, if you have some basis for Rn that has n vectors in it, to find coordinates relative to a basis, first you'd write down this matrix, you'd put all these vectors into a matrix, and then you'd take the inverse of that matrix, and then you'd multiply whatever vector you were starting with, maybe it's x, multiply that by this matrix. And this would tell you the coordinates of x relative to this basis. But this is a lot of work, especially if there are a lot of vectors in your basis. If you're working in a high-dimensional space, finding an inverse matrix is actually a lot of computation. But for orthonormal bases, it's much easier to find the coordinates relative to a basis. So in fact, if you have any vector in your subspace V, that vector is just the sum of the vector dotted with all of your basis vectors times the basis vectors, right? Computing these dot products is actually pretty straightforward. The formula for a dot product is really nice and easy to compute. So if this is true, and it will be, this is much, much less work to find the coordinates relative to the basis than this computation here involving a matrix inverse. So let's just check that this is really true. So we know that it's possible to write V in terms of this basis. So it's possible to write V as the sum from I to k of AI VI. Okay, and we just need to know what are these AI. So hopefully it'll turn out to be these dot products, but let's check. So what we can do is for each I, take the dot product with VI. So what is, I guess I should take the dot product with VJ. So what do we get when we dot this with VJ? Well, if we dot with VJ on the left, we have to dot with VJ on the right. Okay, dotted with sum from I equals 1 to k, AI VI. Okay, now on the right-hand side, we can distribute this dot product into this sum. So that gives us Vj dot V equals the sum from I equals 1 to k, AI Vj dot Vi. Okay, so the left-hand side is still Vj dot V. And on the right-hand side, well, most terms in this sum disappear because remember, whenever these two vectors, Vj and Vi, are actually different vectors, their dot product is 0 because we're working with an orthonormal basis. And in an orthonormal basis, different basis vectors are orthogonal. So their dot product is 0. So the only term of this sum that survives is the term where Vj and Vi are actually the same vector. And that in that case, Vi is actually equal to Vj. And so we just get the term Vj dot Vj. Right? Every other term in the sum disappears. And then there's this coefficient out front, which is a sub I. But remember, I is equal to j, because that's the only term that survived. So we need a j here. Okay? But now this dot product, the only dot product that survived on the right-hand side, has vj dot vj, but remember, this basis is orthonormal, so every basis vector has length 1, and so vj dot vj is just 1. So it disappears. We just are left with vj, or a sub j on the right. And notice that this is exactly what we wanted to prove, right? We proved that the jth coordinate of v relative to this basis is vj dot v, and that's what this is claiming right here. So this is really one of the main reasons that orthonormal bases are so nice. It's because finding coordinates relative to orthonormal bases is very, very straightforward. It's a very easy computation. All right, the second thing that's nice about orthonormal bases is that if you have a basis for not a subspace of Rn, but for the entire space, then if you stuff all of your basis vectors into a matrix as columns, then that matrix turns out to be something called orthogonal. Its transpose is equal to its inverse. Orthogonal matrices, in addition to having this really nice property that the transpose is the same as the inverse, it turns out the determinant of any orthogonal matrix is either 1 or minus 1. So let's check why this is true. So the matrix that we're talking about is, we're just stuffing all of these basis vectors into a matrix like this. And so let's look at the transpose. Well, the transpose would have, instead of having these basis vectors as columns, it would have them as rows. So we would write v1 transpose, right? That's the first row, and then on down to the last row, which is vn transpose. So let's check if these are genuinely inverses. Well, to check that, what we can do is just multiply A transpose by A and see if we get the identity. So this, let's see, A transpose is v1 transpose down to vn transpose as rows, and then A is v1 down to vn as columns. Okay, and remember, one way to express what a matrix product does is it takes columns of the matrix on the right dotted with rows of the matrix on the left. And if you think about what that does is, in the ijth position, it just gives you vi dotted with vj. But all the vi's and vj's, they're all perpendicular except when vi is equal to vj, in which case this dot product is 1. So this matrix is going to have a 1 wherever I is equal to j, and that's down the diagonal, and it's going to have a 0 whenever I is not equal to j, and that's going to be above and below the diagonal. But this is just the identity matrix. So A transpose times A is the identity, but also A transpose A and A are both square, and if a product of square matrices is the identity, then the product the other way around, A transpose, is also the identity. So that proves that for an orthogonal matrix, that proves that for this matrix that we got by taking our orthonormal basis and putting it in as columns, it proves that A transpose is the inverse of A. So that proves this first thing. This matrix we got is orthogonal. Its transpose is equal to its inverse. Well, now let's see why the determinant of an orthogonal matrix has to be plus or minus 1. Well, let's think about the determinant of A transpose A. But we just said that A transpose A is equal to the identity because A transpose is A inverse. So this is the determinant of the identity matrix, but that's 1. But in this determinant here, determinant of A transpose A, we have a product. And one of the key things about the determinant is that the determinant of a product is the product of the determinants. So we can rewrite this as the determinant of A transpose times the determinant of A. But another thing that we know about the determinant is that the determinant of a matrix and its transpose are the same. So the determinant of A transpose is actually the same as the determinant of A. And so we get just the determinant of A squared. So 1 is the determinant of A squared. So that means the determinant of A has to be either plus or minus 1. Okay. The last interesting thing about orthonormal bases is that this linear transformation that gives us the coordinates, and also actually the inverse of this matrix, is an isometry. An isometry is an isomorphism that doesn't change the length of vectors. Right? Most isomorphisms between Euclidean spaces do change the length of vectors, but isometries keep the length of vectors the same. So let's see why that's the case. And it's actually a little easier to, I guess, well, it's a little easier to work with the inverse of this coordinate transformation. So remember that one of the things that we proved for this, the inverse of this coordinate transformation, is that its matrix is just the matrix you get by putting your basis vectors into a matrix as columns. So in other words, it's this A that we were working with earlier. That means that the matrix for this coordinate transformation, C sub B, is A inverse. But remember, if this basis is orthonormal, then the matrix A is orthogonal, which means that its inverse is just its transpose. Okay, so let's check now that this linear transformation doesn't change the length of vectors. So what I mean by doesn't change the length of vectors, what this really means is that the magnitude of V should be equal to the magnitude after you do this transformation. Okay. So let's check what these magnitudes are. Well, it's a little easier to work with the squares of the magnitudes, right? So let's work with the squares instead. Well, what is the square of the magnitude of V? Well, that's just V dot V. And remember, another way to write this is V transpose times V. Okay, what about this one? Well, remember that this coordinate transformation, it's a linear transformation whose matrix is A transpose. So C sub B applied to V, this is really A transpose times V. Okay. So what is the square of the magnitude? Well, that's the dot product of this vector with itself. So A transpose V dotted with A transpose V. Right? But another way to write the dot product is that it's the transpose of this vector, so A transpose V transpose times A transpose V. Okay, but what is A transpose V transpose? That's V transpose, A transpose transpose, and then times A transpose V. Okay, so this is V transpose, A transpose transpose, so that's A, times A transpose times V. And then, right here, A transpose. Remember that A is orthogonal, so A transpose is A inverse. So A transpose A is just the identity matrix, right? So in the middle here, we have the identity, so we can just stop writing it. So this is V transpose V, right? So here we proved that the magnitude after this transformation is equal to the magnitude before this transformation, right? So this proves that this coordinate transformation, or indeed any linear transformation represented by an orthogonal matrix, doesn't change the length of vectors. And actually, it's even better than that. Not only does it not change the length of vectors, it doesn't change the dot product of vectors. So suppose we have two vectors, v and w, in Rn, and suppose we have an orthogonal matrix, right, or a linear transformation represented by an orthogonal matrix, so that A transpose is equal to A inverse. Okay, then let's compute the dot product of these two vectors before and after applying this linear transformation. Right? After the linear transformation, the dot product is this, AV dotted with AW. Before the linear transformation, it's just V dot W. Okay, well, let's compare these two. AV dotted with AW, we can write that as AV transpose dotted with AW, sorry, not dotted with, AV transpose times AW, but AV transpose is V transpose A transpose times AW, and A transpose A is the identity. So again, we just get V transpose W, but that's equal to V dot W. So you can see that this shows that for any linear transformation represented by an orthogonal matrix, the dot product before and after the transformation is the same. That means that these linear transformations don't change lengths and they don't change angles. And that's why we use the term isometry for this kind of linear transformation. Isometry, or iso means same, metry is measurement, so an isometry gives you the same measurements before and after the linear transformation. So you can see that orthonormal bases have lots of nice properties. So really they're the best kind of basis. It's very easy to write coordinates in terms of orthonormal bases, and they also always give you orthogonal matrices and isometries for linear transformations. For an example of an orthogonal matrix, let's consider this rotation matrix. Now, if you think about rotation in the plane, if you rotate some vectors, the lengths of the vectors don't change. And also, if you have two vectors in the plane and you rotate both of them through the same angle, the angle between them doesn't change. And that means that a rotation should be an isometry, because before and after rotation, lengths are the same and angles are the same. That means that any matrix representing a rotation ought to be orthogonal. So let's check if it is. Remember, an orthogonal matrix is a matrix whose transpose is equal to its inverse. Okay, so it's actually very easy to check if a matrix is orthogonal. You just have to calculate A transpose A and check, do I get the identity? Because if you did get the identity, that means A transpose was really the inverse. So let's do that in this case. So the transpose of this matrix is cosine theta sine theta minus sine theta cosine theta. And then A itself is cosine theta minus sine theta cosine theta. Okay, now we have to work out this matrix product. So let's see, first row, first position, cosine squared theta plus sine squared theta. Okay, that's looking promising because that's equal to 1. That's just the Pythagorean identity. And this upper right, we're going to get, let's see, second column times first row. So minus cosine theta sine theta, and then plus cosine theta sine theta. So those cancel and we just get a 0 in that position. In the lower left, so second row, first column, we're going to get, looks like minus cosine theta sine theta, and then plus cosine theta sine theta again. So that's 0. And then in the lower right, let's see, second row, second column, we get minus sine times minus sine. So that's plus, because it's negative times negative, so plus sine squared theta, plus, and then cosine times cosine, so cosine squared theta. And sure enough, that's 1. So we did get the identity here, and that means that this rotation matrix is orthogonal, because its transpose is equal to its inverse. Of course, any rotation matrix is going to be, any rotation is an isometry, and so any rotation matrix will be orthogonal, because an isometry is always represented by an orthogonal matrix.